Hello guys, welcome to this new video. So now we're going to go through the November 23 paper 3, and within that the relativity questions that are also applicable to the current 2025 syllabus. So in this question 3, the first relativity question in this paper, we have muons traveling parallel to each other. And well, the first couple of questions are not part of the syllabus anymore, so we will just skip over that. However, the last part of this question is where we're told that in muon decay experiments, so these are still part of the syllabus, we're told that muons are produced high in the Earth's atmosphere and move towards the ground at speeds close to the speed of light. Detectors on the ground record the arrival of muons, and we need to outline how these experiments provide support for time dilation. So the main thing is that muons have a very short lifetime. They decay very quickly into electrons. So that's the first point we need to write down. So muons decay into electrons very quickly. They have a very short half-life. And so what we would assume is that if they're very high above in the atmosphere on the Earth, we would detect the arrival of muons, of electrons, because the muons decay very quickly and then the electrons will be just traveling down back to Earth. However, what we record with the experiment is that actually muons are arriving, not electrons. So what we can say is that with no relativity, muons wouldn't really arrive at the Earth's surface. And what we actually see is that what the experiments show is that actually we detect muons arriving and not electrons. So muons arrive, not electrons. So what this means is that the half-life or the lifetime of the muon has actually increased according to the Earth observer. Because if we would just look at the rest lifetime of the muon, that would be a much shorter time compared to how much time the muon travels from the atmosphere to the ground. And therefore, we can say that the lifetime of muons increased according to Earth observers. And well, this is the phenomenon of time dilation, and then this is what we had to kind of explain over here in this part. And then in question 4, we have two clocks A and B. They were told that they have been synchronized and they're a distance d away from each other, and we need to suggest a way we can synchronize these clocks. So what I would say the easiest way to do this is that both clocks are set to read 0 at the same time in the same position in space. So both clocks read 0 at the origin. One is moved, and then we take one of these clocks and move it to to a distance d away. So move a clock distance d away, and the only thing we need to watch out for is that this has to be done at very small velocities, because if we move it quickly, then relativistic effects will take into account, time dilation will occur, and therefore they will not be synchronized anymore. They will not be showing the same time. So we need to do this at very small velocities, so these relativistic effects don't really take place. All right. And then the third relativity question in this paper, we have a spacecraft that is leaving Earth with a speed of 0.8 c relative to the Earth, and it's on its way to a planet that is 12 light years away according to Earth measurements. So this is very important. We need to calculate the time of arrival of the spacecraft and the planet according to the Earth. So what the Earth sees is that the spacecraft simply travels 12 light years with this speed. Therefore, we can calculate the time as velocity divided the distance divided by the velocity, using simple kinematics here. So we have 12 light years, and that's going to be divided by 0.8 times c, and this will give us 15 years. So that's about it. And then for the spacecraft, the thing is that this will be this 12 light years is the proper length measured, because it's measured by the Earth observers. It's measured by the observers that are at rest with respect to this length. However, the spacecraft is going to observe a different length and therefore a different time, because he will have to take into account relativistic effects. So for this we need to first calculate the gamma factor. That's simply 1 over the square root of 1 minus 0.8 squared. This will be 5 over 3. And then we know that time is equal to the proper time divided by the gamma factor. The proper time is what's measured by the Earth observers because they're at rest. And this will have to be divided by 5 over 3. And this will give us 9 years. Alright. And then we're told that on its way to the planet, the spacecraft moves past the cargo ship returning to Earth. The proper length of the cargo ship is 992 meters, and the speed is 0.6 relative to the Earth. We need to state what is meant by proper length. So proper length is simply the length, or we could also say it's let's just say it's the length of the object in its rest frame. We could also say it's the longest possible length we could measure. In part 2, we need to show that the speed of the cargo ship relative to the spacecraft is 0.946 c. So here we need to use the relative velocity formula, which is u prime is equal to u minus v over 1 minus uv over c squared. We just need to take into account the signs. So we need to find u prime of the cargo ship. So u is going to be 0.6 c. However, since it's traveling to the left, it's going to have to be negative 0.6 c relative to the spacecraft. And then we minus v, which is minus 0.8 c. And this is all divided by 1. And then this negative also becomes a plus because u is negative. So this will be a 0.8 times 0.6 divided by c. And this will give us 0.946 c. We need to calculate the length of the cargo ship according to the spacecraft. So again, we just use the fact that the length is the proper length divided by the gamma factor. The proper length we're told is 992 meters, and we divide it by, we need to watch out here because this is not the same gamma factor that we have calculated all the way back, because we have to calculate the length of the ship according to the spacecraft. And as we have just calculated, the spacecraft is moving at a relative speed of 0.946 c. So that's assuming that this would be at rest and the spacecraft would be moving. So the new gamma factor is going to be 1 over, 1 over the square root of 1 minus 0.946 squared. And if we do this, we get 322 meters. And then part C, we're told as the spacecraft approaches the cargo ship, a light signal is emitted from the front of the cargo ship towards the back. The situation is represented in the space-time diagram. Yes, F and B. In part 1, we need to construct lines on a space-time diagram to show the arrival of the light signal at the back of the cargo ship. So what we need to take into account here is that the cargo ship is at rest. So the position of B is not going to change. And that's why we can draw a line like this, because as a function of time, the position of B is always going to be at the same position. So its position doesn't change. And well, this beam is going to travel at the speed of light. And we have to draw the word line of a photon traveling from F and the speed of it is just a photon, therefore it will have to be a 45-degree line. Therefore we can make a 45-degree line by going through these diagonals. So if we connect these points, we get right over here. So this will be position A. Again, because we have to draw a photon, which has to make an angle of 45 degrees here because it travels with the speed of light. And then part 2, we need to determine the time it takes the signal to arrive at the back of the cargo ship according to the spacecraft. So for this, we have to use the Lorentz transformation for t prime. This will be t minus vx over c squared. So we know that the gamma factor is just going to be basically what we have calculated up here. So that will just be 1 over the square root of 1 minus 0.946 squared. This will be multiplied by basically the time. So the time it takes for the signal to reach in the rest frame. So that will just be distance over speed. Right, so the rest distance, so the normal t, the time in the cargo ship's frame is just going to be the distance divided by the speed that the light is traveling at. And then from this, we need to subtract the relative speed of the spacecraft, which is going to be minus 0.946 because it is approaching the cargo ship. And then we multiply this by the normal distance, so 992, and we divide it by c like this. There's also c here, we can write a c squared like this. It doesn't really matter. And if we solve this, we get that this is 1.98 times 10 to the minus 5 seconds, like this. And also one thing here, obviously this is going to be negative here because the numerator is negative. It's only asking for the speed, so the magnitude is actually enough to stay here. We don't need to deduce the direction of it, but to be precise, we could put a negative sign here as well. And then the remaining relativity questions in this topic are all from the old syllabus. So this is going to be the end of this video.